Hello friends, welcome to G-Centric. So in this lecture we will start with a new chapter, that is passive filters. Okay, so here we have, in this network theory we are going to learn only about the passive filters. But if you see in the filter section, there are two types. Okay, basically one is active filters, okay, and passive filters. Okay, so why we are studying only passive filter in this lecture is that because first of all, in active we will be having RLC, okay. With this resistor or inductor or capacitor, we will connect an op-amp, okay. So when we connect these passive elements with op-amp, then it becomes active filters, which is the section of analog electronics. Okay, so this we will study in the analog electronics part. But here in the passive filter, we will just identify RLC, okay. Only these fundamental elements will be present and we have to identify what type of filter it is. From GATE point of view, for electrical branch it is very less, okay. They haven't asked questions, okay, but in EC and instrumentation they might ask, especially for the electronics branch. This will be a important topic. 1 mark or 2 mark questions we will able to see in this from this section. Okay, so in passive only we have got two sections or two types of filters. One is low pass filter, second one is high pass filters. Okay, so first we will study about the low pass filter and then we will go on with the high pass filter. In the low pass filter, how do we identify the circuit, whether it is a low pass or high pass? Okay, so basically what does this low pass mean? Okay, it will allow the lower range of frequencies compared to higher range of frequencies. In high pass filter, the filter will allow higher range of frequencies than low pass of frequencies. Suppose if you consider 0 and 1, this to be the low pass filter or low pass, you can take it as lower range of frequency, okay, and 1 as higher range of frequency, okay. So when you consider this, how will the circuit allow this value, okay, what will be the output voltage, and when it is 1 it will be a high pass filter. Okay, so in the filter section, if you plot a graph, if here it is 0 and suppose, sorry, this is 1, okay, and this is omega, and here something we have got an output for the circuit. Okay, here in this range, let us consider this is cutoff frequency. Okay, omega c is the cutoff frequency. If we understood this one, from where it will judge whether it is a low pass filter or high pass filter. Okay, this we have seen already in the resonance section, right? So now, if in this range, if the plot comes something like this, then it is allowing the lower range of frequency. Okay, lower range frequency. Because higher range of frequency, which we are taking it up to infinite. Okay, instead of 1, let us take this as infinite. Okay, let us define this as infinite, so there won't be any confusion. So infinite is 0, but we have here from 0 to 1. Okay, so this is low pass frequency. If the same graph was like this, then it is high pass filter because it is allowing the infinite range of frequencies. Lower range is 0. Okay, so now we will draw the circuits for low pass filter and high pass filter. Okay, so first we will start with the low pass filter. So remember, in the low pass filter we have resistor and capacitor. Okay, so from where there is only this difference. Okay, we will take only a simple circuit to understand. We will write it with low pass filter. Okay, so if this is a resistor, let us take it as R, okay, and we have here input voltage Vi and capacitor is connected, from where we are taking the output V0. So this is C. So low pass filter, basically we have decided that whatever the output voltage we are drawing, it should be from the capacitor. Okay, so then only we will call it as the low pass filter. So now we will prove how it is a low pass filter. So before that, we will convert the circuit into Laplace domain. Okay, so this is Vi of S. For R it is nothing, V0 of S, and this will be 1 upon Cs, right? We will now take the transfer function for this one. So what is transfer function? Output upon input in the Laplace domain. So V0 upon Vi of S. Let us define this as H of S. Okay, so if you have to take the output voltage across this capacitor, then we will apply the voltage division rule. So V0 of S will be equal to 1 by Cs 1 plus 1 by R plus 1 by Cs, okay, into Vi of S. Now if I rearrange this one, V0 of S divided by V of S, which is equal to H of S, will be equal to 1 upon 1 plus RCS. Now if I take the RC common, okay, let me take RC common. So when I take RC as common, I will get 1 by 1 plus S times of RC. If I take this up, it will be 1 upon RC, right? If I take this RC common and if I divide this by 1 by RC, it is same. I will get the equation back. Okay. So now I will put, or you can take even in this, we will take this as outside only. Okay. RC, okay, S plus 1 by RC. Okay. So this RC will go up. Okay. 1 upon RC. Right. Now I will put S is equal to J omega. So H of J omega will be equal to 1 upon RC J omega plus 1 by RC. Okay. Now I will take the magnitude of this H of J omega. H of J omega magnitude. So what I will get? This will be 1 upon RC divided by omega square plus 1 by RC whole square. Correct? So this is the output equation that we have got for this low pass filter. Now to identify the what it is, okay, how it is a low pass filter, first we will take omega equal to 0. Okay, low pass frequency, and once for omega equal to infinite. Okay, that is high frequency. Now substitute omega equal to 0 over here. So you will get 1 by RC, 1 by RC, that is equal to 1. So H of J omega will be equal to 1. Magnitude is 1, right? So now here when you put infinity, right, omega square 1 upon infinite. Okay, so this will be, if you take this as negligible, you will get omega equal to, H of J omega equal to 0. Okay, the magnitude is 0. Now if I draw the plot for this or graph, what I will get? Okay, so this is magnitude of H of J omega and this is omega. Okay, for omega equal to 0, I am getting the magnitude as 1. Okay, for omega equal to infinite, I am getting J omega, magnitude of H of J omega is equal to 0. So somewhere if I take the cutoff frequency over here, okay, where it stops, basically this omega cutoff frequency, or you can call it as roll off frequency. Basically this cutoff frequency is nothing but a gate, whether to see it's a low pass filter or a high pass filter. So if I take over here, my ideal graph will be like this, right? So it is allowing the lower band than the higher band frequencies. So I can conclude that it is the low pass filter. This is one of the simple control system, taking the Laplace transform from the control system, right? Okay, and applying the voltage division rule. But now if that is a complicated circuit, you cannot solve this one. So we have got another method for this. Okay, we will see how we can easily solve this one. Second method. Okay, why we are using second method? If you have got the combinations of RLC with a complex circuit, you cannot use this type of method because it will take your time, consume your time, and most of the times you will not get the answer also. Okay, so second method is, first we will take omega equal to 0. So at omega equal to 0, we will see that XL equal to omega L and XC is equal to 1 by omega C. So put omega equal to 0, you will get 0 ohms. Here put XC is equal to 0, you will get infinite ohm. So what does this 0 ohm indicate? It means that it is a short circuit condition. Okay, when it is infinite ohms, it means no current will flow, it is open circuit. Okay, so this is the thing. Next, coming for the when it was 0. Now we'll evaluate for higher frequency. When omega equal to infinite, XL is equal to omega L, you will get infinite ohms. So, okay, so when you get infinite ohm, it is open circuit. When we have omega equal to infinite condition. Okay, next XC is equal to 1 upon omega C. 1 upon infinite is 0 ohms. So what you will get, the condition is short circuit. Now how do we analyze this circuit? Okay, so if I redraw the circuit at omega equal to 0. So at omega equal to 0, what is capacitor? It is infinite ohm, means we have to open the circuit. Okay, if I take this one, this is R and we have here open circuit. So this is Vi of S and here we have V0 of S. So what does this mean? Here it is 0 drop, it is open current, there is no current flowing in the circuit, right? So this condition gives you Vi of S equal to V0 of S when at omega equal to 0. Okay, so you will get this as 1. Next we will see for, okay, I'll rub this part. We will see the condition for omega equal to infinite. Okay, so at omega equal to infinite, capacitor will behave like, okay, this is C, 0 ohms. That means it is a short circuit condition. So how will you draw this one? We have a resistor, short circuit. Okay, this is Vi of S and here is the output V0 of S. So when it is short circuit, it means there is no potential difference. So this is also 0 volt, this is also 0 volts. So V0 of S is equal to 0 volt. So you are seeing in this graph that at infinite value, we are getting the output as 0 volt. So it means it's only allowing the lower band frequencies, not the higher band of frequencies. Okay. So next, similarly, we will solve for the low pass, high pass filter as well. Before that, we will draw the Bode plot for this one. Okay, so basically it will go like this and come down like this. So this is negative slope, so it will be minus dB. Okay, and here is one more thing. Now this is not the, this is the ideal graph, but in reality, okay, practically speaking, this will come down somewhere here like this. Okay, and to find the cutoff frequency, so let us take this as 1 by root 2 times of the magnitude. That will be your cutoff frequency range. Suppose here it is 0.707. 1 by root 2 will give you 0.007. Here will be our cutoff frequency practically. Okay. So this is the Bode plot. Here is omega. Bode plot is basically between h of j omega versus frequency. Okay, magnitude versus frequency. Okay, so this is about the low pass filter. Now we will see the high pass filter. Okay, everything will be same. We were drawing the output voltage from the capacitor, but in this case, in the high pass filter, we will draw the output voltage from resistor. Okay, so now we will see, and after this we will see some more questions, some questions based on this high pass and low pass filter. And in the next lecture, we will see about the all band pass filter. Okay. So now here only I will modify this one. Okay. So this is capacitor over here. Okay. This is C and here we have resistor. Okay. Again similarly. Okay. So this is for high pass. We will convert this into Laplace domain. This will be 1 upon Cs, this is R and here V0 of S. Now H of S will take the transfer function. Okay, V0 of S upon Vi of S. Apply the voltage division rule, you will get R upon 1 R plus 1 by Cs into Vi of S, and I have taken here Vi of S. So when you rearrange this one, you will get RCS. Okay, so this CS will go up, 1 plus RCS. Okay, right? So this will be 1 RCS. So is it RCS? Yes, RCS. Okay, same now we will take the magnitude of this one, put S equal to J omega. Okay, so when you put H of J omega, you can take here again RC as common. Okay, so when you take here RC as common, you will get 1 by RC plus S. Okay, so this S gets cancelled. So this is S upon S plus 1 by RC. Okay, so the time constant is RC, 1 upon RC. Cutoff frequency will be 1 upon RC. Right? So then we will take the magnitude now. Okay, put J omega over here. So when you are taking magnitude, do not put J. So this will be, what is it? The S will be omega square plus 1 upon RC square. So now we will analyze the circuit. Okay, so for omega equal to 0, put omega equal to 0, you will get H of S as 0. Okay, next put omega equal to infinite. Okay, so for some time, if you assume this 1 by RC is negligible, it means omega, this omega square will come out of the root, omega by omega will give you 1. Okay, so H of J omega will be 1. So now if you see here, this omega equal to 0, which is a low pass frequency range, we are getting the output as 0, whereas for higher range of frequency we are getting 1 as our output. It means it's a high pass filter. So our diagram will be, graph will be, if this is omega and here we have H of J omega. Okay, somewhere if here it is a cutoff frequency, we will get this graph. Okay, this is 1. This is ideally, practically what we'll get, somewhere it starts over here, okay, then it goes something like this. Fine, if this is only, let us assume cutoff frequency at 0.707. Fine, this is high pass filter. Now we will see our second method. Okay, in the second method, we will put omega equal to 0. We will analyze only for capacitor because only we have got a capacitor, there is no inductor. So at omega equal to 0, what we are getting? 1 by XC is equal to 1 by omega C. So infinite ohm, it means open circuit. Okay. Similarly for omega equal to infinite, XC will be equal to 0 ohms. So it means short circuit. Okay, it is the condition for the short circuit. Now we will draw the diagram. Okay, so first at omega equal to 0, how does the capacitor behave? Open circuit. Okay, draw the open circuit now. Okay, keep this as it is. Then this is R. Okay, plus minus. We have got here Vi of S. This is R. And this is V naught of S. So if you see there is no current flowing from here, this is also open circuit, this is also open circuit. So there will be 0 volt drop. So V naught of S will be equal to how much? Vi of, so, okay, right. So this is also open circuit. So you will get this as Vi of S. Okay. So if I am not wrong, this is infinite. So when you put 0, you will get open circuit. Okay. So if it is open circuit, just a minute. Okay, so here there is nothing, 0 voltage drop, so you will get 0 volt. So basically if it is 0 volt, it means it's like there is no potential difference between the points. Okay, so this is 0 volt. Next, second condition is at omega equal to infinite. Okay, so at omega equal to infinite, XC will behave like a short circuit condition. Okay, so redraw this one. This is short circuit and here we have Vi of S, this is R and here is plus minus V naught of S. Okay, so now this will be, if there is some will, okay, let us take this as also, this voltage will only appear over here, and this voltage is equal to Vi of S. Okay, so basically V naught of S by Vi of S is equal to 1. Okay, so this is what you are getting over here. From 1 you are getting the higher band of frequencies than the lower band of frequency ranges. So this is the easiest method to identify what type of filter it is. Now we will take some questions based on this concept. Okay, so coming to this question number 251, we have to find what type of filter it is. So we will apply our method to find this one. Okay, so at only inductor is there, so we will analyze only for inductor. So at omega equal to 0, XL is omega L, which means 0 ohms, short circuit. Condition is short circuit. So at omega equal to infinite, XL is equal to infinite, it is open circuit. Okay, so now we will draw the graph for this one. Okay, H of j omega. Now, so if it is omega equal to 0 ohm, okay, omega L is 0 ohm. So it will be short circuit from here to here, right? So when it is short circuit, our output is V naught equal to 0 volts. Okay, when V naught of S is equal to 0 volt, when we have omega equal to 0. So at omega equal to infinite, we have open circuit. Okay, when it is open circuit, directly we have Vi of S equal to output voltage, right? So our graph will be somewhat from here. Okay, for lower band frequencies, we have output voltage 0. Okay, and here it is 1 for input voltage, that is, sorry, a higher range of frequencies, that is omega equal to infinite. So what type of filter it is? High pass filter. Okay, coming to this one, we have to analyze for this. Now we will analyze it for both. Omega equal to 0, XL equal to how much? So omega L, we have 0 ohms, right? So it is short circuit. So what will be XC? 1 upon omega C, infinite ohm, open circuit. Okay. Next we have for omega equal to infinite, XL is equal to infinite ohm, so it is open circuit. Next XC is equal to 1 upon omega C, we have 0 ohms, so it is short circuit. Okay, so now see here, first we will go for omega equal to 0 ohms. Okay, we will draw the circuit for this one. We have here both L and C. Okay, so now at omega equal to 0, it is short circuit and this is open circuit. So there is no current flowing in this also, in this also. So V naught we are getting 0 for omega equal to 0. Okay, next we will analyze for infinite ohm. So XL will be open circuit and this will be short circuit. So now here there is current flow is 0. Okay, there is no voltage drop for this also, here also, right? So what we are getting, V naught equal to Vi of S. Okay, when we have omega equal to infinite. So it means that we are getting again for high pass frequencies. So it is a high pass filter. Okay, I hope you have understood this concept. So in the next lecture we will see for all band frequency filters. Thank you.